In this video, I'm going to go through some problems involving work and work done by forces. Okay, so in this first problem, we have a 150-gram baseball that is thrown straight up 7.4 meters in the air. And we want to find the work done by gravity on the way up, on the way down, and the total work done by gravity while the baseball is in the air. So the baseball is going to be thrown up. It's going to get to the top. This distance is going to be 7.4 meters. And then it's going to come back down. Okay, so our definition for work is the work done by a force is that force times the displacement of the object times cosine of the angle between the force and the displacement. So on the way up, the ball has weight, which is pointing straight down towards the earth, but it's moving up, so its displacement, d, or delta y in this case, is going to be straight up. So they are going to be 180 degrees apart. So if we look at the baseball on the way up, the work is done by gravity. So this is, let me draw this as a big W, make sure not to get confused. The work is force times distance over cosine. In this case, this force is the weight, or little w, times the displacement. I'm going to call this delta y since it's going up. And the angle between these two is 180 degrees since they're in opposite directions. So cosine of 180. But that's pretty easy to deal with. Cosine of 180 is just minus 1. So we get minus, I'm going to write mg for the weight, okay, since it gave us the mass, times delta y. And if we plug all of this in, we have minus a 0.15 kilogram baseball times 9.8 meters per second squared times a vertical distance of 7.4 meters. And if we plug that in, we get a negative 10.9 joules. Okay, so now if we do the same thing on the way down, maybe I'll do this in a different color. So on the way down, we have the same expression for work, force times distance times the cosine of the angle between them. And on the way down, the weight is still going to be down, but now the baseball is also moving down. So our displacement, or delta y, is going to be in the same direction as the weight. So we have the weight times delta y times cosine of the angle between them, but this time it is 0. And cosine of 0 is just 1, so we get mg delta y. Or this is going to be the exact same thing we got before, except now we don't have this minus sign, so this is going to equal 10.9 joules. Okay, so if we were to look at the total work, it would be done by gravity. It would be, that's right, work total is the work done by gravity on the way up plus the work done by gravity on the way down. And that's going to equal 0. Okay, so we lose 10.9 joules on the way up. We gain 10.9 joules on the way down. Okay, or to say it more precisely, gravity does work against us on the way up, removing 10.9 joules of energy from the baseball. And then it does work adding 10.9 joules of energy on the way down. And so that corresponds to the baseball slowing down on the way up and then speeding back up on the way down. And then when it gets back to where it started, it has the same amount of energy as it started with. It's at the same height, so it has the same amount of potential energy. And it's going at the same speed, just down, so it has the same amount of kinetic energy. So the total work done on the full trip should be 0. So in this next problem, we have a 55 kilogram man that rides an escalator, which makes an angle of 30 degrees with the horizontal. If the escalator takes him to a second floor that is 21 meters above the ground, find the work done by gravity, the work done by the normal force from the escalator, and the work done by friction on his feet. So I'm going to start by drawing a picture of the escalator. So it goes up. It makes an angle of 30 degrees with the horizontal. And it takes the man to a height of 21 meters. So this is going to be our delta y. I guess I can draw the man on the steps. And in part A, we're asked to find the work done by gravity. So in this case, our weight, or the force of gravity, is going to be straight down. Okay? And our formula for work is the work done by force is the component of the force that's parallel to the displacement. So only forces that are parallel to the displacement are going to do work. And so we really don't care about, since the weight is going straight down, we don't care about the left and right motion of the man. We only care about his displacement that is parallel. Okay, in this case, that is his displacement up and down, and he goes up 21 meters. Okay, and since these are anti-parallel, or they're in opposite directions, we end up picking up a minus sign. So when the force and the displacement are in opposite directions, we get a minus sign. So this is minus the weight times the displacement that's parallel, or in this case delta y, or minus mg delta y. So that's minus 55 kilograms times 9.8 meters per second squared times the delta y, or 21 meters. And so the work done by gravity is minus 11,320 joules, or minus 11.32 kilojoules. Okay, now if we go to part B, the work done by the normal force from the escalator step, now the normal force is going to push up. Okay, and then the displacement is also going to be up. So now they're in the same direction, so the work is going to be positive. Okay, but we don't know what the normal force is yet. Okay, so let me go ahead and write our equation. The work is the parallel component of the force to the displacement. And this is going to equal the normal force times the displacement, or in this case, I'll write delta y. So we need to find the normal force. So one thing we can do is look at Newton's laws. If we draw these on a free body diagram, we have the normal force going up and then the weight going down. Okay, so we have the man kind of sitting on one of the steps. Normal force from the step is pushing him up, his weight is pulling him down. And so if you sum up the forces in the y direction, okay, he's not accelerating through the step or off the step. So relative to the step, he's not moving. So you have n minus w, or minus the weight, is equal to 0. And so this tells us the normal force is just equal to the weight. So in this case, we can just replace the normal force with mg and then multiply that by delta y. And this is the same thing we got up here, just now it's positive. So now we got a positive 11,200 joules, or positive 11.32 kilojoules. Okay, and if we do part C, the work done by friction on his feet, this again is the work done by the force parallel to the displacement. So if we draw our man on the step, first thing you need to notice is he's not moving left or right relative to the step. Okay, so this is going to be 0. There is no friction since there are no forces pushing him left or right. So since no horizontal forces, so the work done by friction is 0. Okay, so he's not actually sliding across the step. The next problem, a 10-kilogram box is pulled 15 meters horizontally across the floor with a 30 Newton force that is 32 degrees above the horizontal. If the coefficient of kinetic friction between the box and the floor is 0.4, find A, the work done by the pulling force, the work done by friction, the work done by gravity, the work done by the normal force, and the total work done. Okay, so this is quite a few parts. But if we draw a picture, we have our box on the floor and it's rough since there's friction. And there's a force pulling at a 32-degree angle above horizontal. So this is our force that is 30 newtons. Our mass is 10 kilograms. Okay, so if we look at our formula for work, for part A, our work is equal to the force that's parallel to the displacement, or another way to write this is force times distance or displacement times cosine of the angle between them. Okay. So if we draw our force, it is at 32 degrees. Our displacement is going to be to the right along the horizontal, and so the force that is 32 degrees, so the force that is 32 degrees above the horizontal is going to also be 32 degrees relative to the displacement. So we can plug all of this in. We have our 30 Newton force. It's going to be displaced 15 meters horizontally, and the angle between them is 32 degrees. If we plug that in, we get 407 joules. Now if we look at part B, we want to find the work done by friction. So the work is again equal to the force parallel to the displacement, or FD cosine theta. In this case, the force is kinetic friction times the displacement. And the displacement, again, is to the right, but this time friction is going to oppose that motion and be to the left. So they are going to be 180 degrees apart, but cosine of 180 is just -1. So we just put a minus sign out front. And then I'll replace the force of kinetic friction by the coefficient of kinetic friction times the normal force. And then that'll be multiplied by the displacement. And so now we just need to find the normal force. So if we draw a free body diagram, we have the normal force pushing up on the box. We have the weight pulling down. We have this force that's at a 32-degree angle. And then we have friction pulling to the right, or to the left, I'm sorry. So if we were to sum up the forces in the y direction, since that's the direction containing the normal force, we get a positive normal force plus the y component of this pulling force, which is going to be opposite of this 32-degree angle. So we get F sine for opposite of 32 degrees, and then minus the weight. And all that's going to equal mass times acceleration in the y direction. But since the box isn't accelerating up off the floor or through the floor, this is just going to equal 0. So if we solve for the normal force, since all of this equals 0, we're going to have the normal force is equal to the weight minus F sine 32 degrees. Okay, since we move these over, okay, or mg minus f sine 32. So if we plug that in, we have minus mu k times the normal force, which is all of this. So mg minus f sine of 32 degrees. And then we still have to multiply by our displacement. So if we plug all of that in, we get minus 0.4. Put some brackets. We have 10 kilograms for the mass times 9.8 meters per second squared minus our 30 Newton force times sine of 32 degrees. Close our brackets, and then we still have our displacement of 15 meters to multiply by. And if we plug all of that in, we get a minus 493 joules of work done by friction. Okay. All right, so now I'm going to erase all this so we can do part C, D, and E. So I'll try to keep my picture. So if we move on to part C, the work done by gravity, again, the work is equal to the force parallel to the displacement. But if we were to draw our forces, the weight is straight down and the displacement is to the right. So there is no component of the weight that's parallel to the displacement because it's completely perpendicular. So this means that the work done by gravity is going to be 0. Okay. If we do part D, the work done by the normal force, we get something very similar. So in this case, the normal force is going to be straight up, and the displacement, again, is to the right. And these are going to be perpendicular to one another. So the work done by the normal force is going to be 0. So finally, if we want to find the total work done, this is going to be the work done by all of these forces, or the work done by the pulling force, plus the work done by friction, plus the work by gravity, plus the work done by the normal force. So if we add all of that together, we had 407 joules of work done by the pulling force, minus 493 joules of work done by friction, plus 0 and 0 for the normal force and gravity, or we have minus 86 joules of work. So in pulling this, we actually lost some energy. And so typically, this is due to friction. So this 86 joules that we lost, we say is dissipated. It's energy that has been dissipated by friction. So this next problem, a 9 kilogram crate is moving at 4.5 meters per second. There's a force that decelerates the crate to a speed of 2.7 meters per second. And we want to find the total work done by this force. So if we just draw a picture, I'm going to draw this crate moving to the right at a speed of 4.5 meters per second. And all we're given is the initial and final speeds of this crate, and we're asked to find the work. So we're going to have to use the work energy theorem, which says the total work done on an object is equal to its change in kinetic energy. Okay, so if we just look at all the forces, there is a normal force acting up, there's the weight of the crate acting down, and then there's some force that is causing it to decelerate. Okay, so some force, I don't know what it is, I'll just call it F. And so since this box, the way I've drawn it, it's moving to the right, there's only one force that is parallel to the displacement. So the normal force or let me write it this way, the work done by the normal force will be 0 since it's perpendicular to the displacement. The work done by the weight, or by gravity, is also going to be 0 since it's perpendicular. So the total work done is going to be all the work done by this force causing the crate to decelerate. Okay? So most likely it's something like friction. So we just need to find the work done by this force, and that's going to be equal to the change in kinetic energy. So delta K is the final kinetic energy minus the initial kinetic energy. And kinetic energy is equal to 1/2 mv squared. So we're going to have 1/2 mv final squared minus 1/2 mv initial squared. And so if we want, we can factor out 1/2 m, since it's in both terms, to make plugging it into a calculator a little bit easier. And then we're ready to plug in. We have 1/2 times the mass, or 9 kilograms, times final velocity, or 2.7 meters per second, all squared, minus the initial velocity, 4.5 meters per second, all squared. And when we plug that in, we get a minus 58.3 joules. Okay, so we lost energy, okay, or we took energy away from the system because it's slowing down. So it was going a little bit faster, so it had more kinetic energy at the beginning. And so we removed some of that energy and caused it to slow down. So it's negative. Since this is the only force actually doing work on the object, this is the work done by our force decelerating the crate. In the next problem, we have a sled weighing 550 newtons that is initially moving at a speed of 12.5 meters per second, and it slides to a stop over a distance of 150 meters, and we're asked to find the coefficient of kinetic friction. So if I draw a picture, I have my sled initially moving at 12.5 meters per second. Okay. And we want to find the coefficient of kinetic friction. So first of all, what's going on in this problem? It's starting with some initial speed of 12.5 meters per second, and then we know it's going to come to a speed of 0 meters per second because it stops. Okay. And it's stopping because there's some force doing work on it, taking energy out of the system or away from this sled. Okay, so that force is most likely friction. And so what we can do is we can use the work energy theorem that says the work done by this force, or the net work done by all the forces, is equal to the change in kinetic energy. And since the only force that's acting in the direction of the displacement is friction, this total work done is just going to be the work done by friction. Okay, so we have friction acting to the left, and the displacement, I like to do that in a different color since it's not a force. So these are two different types of vectors. Okay, we also have a normal force, and we also have a normal force acting up and the weight acting down, but these are perpendicular to the displacement, so they're not doing any work. So all of the work that's taking kinetic energy from the system is going to be from friction. Okay, so this is going to be equal to the final kinetic energy minus the initial kinetic energy. But at the end, it's not moving because it's coming to a stop. So we know the final kinetic energy is going to be 0. So the work done is going to be minus the initial kinetic energy. So this is minus 1/2 mvi squared. But we were given the weight of the sled in newtons, not in, we were not given the mass in kilograms. So we need to come over here and find the mass. So we have the weight equals mg is 550 newtons. So if we solve for the mass, we need to take our weight in newtons and divide by 9.8 meters per second squared, and find the sled weighs or has a mass of 56 kilograms. Now we're ready to plug this in. So we can take this here. We have minus 1/2 56 kilograms times an initial speed of 12 meters per second, or sorry, 12.5 meters per second squared. And we get minus 4,375 joules. Okay, so this was the work done in removing this much kinetic energy. But if we want to find the coefficient of kinetic friction, we need to go to our other expression for work. So the definition of work done by a force is the force times the displacement if it's parallel, okay, or FD cosine theta. But in this case, theta is going to be 180 degrees since the displacement is in the opposite direction of kinetic friction. So this is just going to be minus the force or kinetic friction times our displacement. So I'm going to replace the force of friction with its definition, coefficient of kinetic friction times the normal force, and that's going to be all multiplied by d. So we're going to have to use Newton's laws really quick to find the normal force, but we already know that the forces in the y direction are just the normal force and the weight. So if we sum those up, we have normal force minus the weight. The crate, the sled isn't accelerating up off the ground or through the ground, so there's no acceleration in the y direction. And we get the normal force is equal to the weight. So we can just replace that here. Get minus mu k times the weight times the distance. So we have minus mu k times the weight times the distance equal to the change in kinetic energy, or minus 4,375 joules. You also could have just plugged this in all at once, but I'm doing it in 2 steps. So now if we solve for the coefficient of kinetic friction, these minus signs are going to cancel, which is good. And we have 4,375 joules over the weight of the sled, 550 newtons, times the distance of 150 meters. And that gives us a coefficient of kinetic friction of 0.16. The next problem, a spring has a spring force constant of 400 newtons per meter. If you spend 8 joules of work to stretch the spring, find how much the spring will stretch. Okay, so the work done by a spring is equal to 1/2 kx squared, or the spring constant, times the displacement of the spring squared. So x here is just the displacement of the spring. So if we solve for the displacement of the spring, we need to multiply by 2 on both sides, divide by k, and then take the square root. And if we do that and then plug in, we have 2 times the work done, or 8 joules. So 8 joules of energy was spent over a spring constant of 400 newtons per meter. If we plug all that in, we get 0.2 meters, or 20 centimeters. Okay, so you spent 8 joules of energy stretching or compressing the spring 20 centimeters. Okay, in this final problem on work, we have that you are skiing at a speed of 7 meters per second on a frictionless flat patch of snow. You then cross a rough stretch of snow for 4 meters and return to the frictionless snow at a speed of 3.2 meters per second. And we want to find the coefficient of kinetic friction for the rough snow. Okay, so let's draw a picture. We're skiing, and we're starting at a speed of 7 meters per second, but we run into a rough patch that's 4 meters. It's going to slow us down due to friction. And when we come out, we're going 3.2 meters per second. So this friction did some work against us to slow us down, and we want to find the coefficient of kinetic friction. So to do this, the first thing we notice is our velocity changed. So there was a change in kinetic energy, and that was done because of the work from friction. So we can use the work energy theorem, which says the work done is equal to the change in kinetic energy. Okay? Or the work is equal to the final kinetic energy minus the initial kinetic energy. Okay? So we need to, one, find the right-hand side just using the velocities of the skier. So we can find the change in kinetic energy, but we also need to find the work done by friction. So the work done by a force is equal to the force times the distance. So we can find the work on the right-hand side done by friction by using our expression for the work. It says the work done by a force is equal to that force times the displacement. Okay, so we can find the kinetic energy just by looking at the velocities. But to find the work, we need to go to the definition of work, which says the work done by a force is equal to that force times the displacement times the cosine of the angle between them, because only forces in the direction of the displacement are going to do work that are parallel to the displacement. So in this case, our force is going to be the force of kinetic friction. Okay, and since we're moving to the right, our displacement is to the right, but friction always opposes our velocity, so kinetic friction is to the left, which means our angle is 180 degrees. So cosine of 180, but cosine of 180 is just minus 1. So we can just write a negative sign. And I'm going to replace our force of kinetic friction with the coefficient of friction times the normal force, and then times the distance. Okay? So in this case, if we use Newton's laws, we're on a flat surface, and if we draw a free body diagram, the normal force of the surface is pushing up, the weight of the skier is pushing down, and since it's not accelerating through the ground or up off of the ground, if we sum up the forces in the y direction and set it equal to 0, we'll find that the normal force is just equal to the weight. Okay? And the weight is just mg. So we can replace our normal force with the weight, or mg, and then we have our distance for our work. Okay? So now I can take this and replace. So now I can take this expression for my work and insert it on the left side over here. Okay, and this is how my coefficient of kinetic friction enters into the picture. So I have minus mu k mg times the distance, and that's going to equal 1/2 mv final squared minus 1/2 mv initial squared. So on the right hand side, just to simplify it, I can factor out a half, and then I can also simplify by noticing that there is a mass in each one of my terms. So I can rewrite this as minus mu k g times d, and then factor out a half on the right hand side, and we get this. Okay, now I can just solve for my coefficient of kinetic friction by dividing by minus GD. So this is going to be VF squared minus VI squared all over, put my minus sign out in front, all over 2 times G times D. Okay, so write this over here, plug in my numbers, I'm going to get a minus, and then our final velocity is going to be 3.2 meters per second when we come out, and that gets squared, minus our initial velocity squared, or 7 meters per second, all over 2 times 9.8 meters per second squared, times our distance of 4 meters. Okay, and it's important to notice that our coefficient of friction should be positive. We have a negative sign here, but because we ended at a slower speed than we started with, our numerator is going to be negative. Okay, so those negative signs are going to go away, which is good. And we're going to get a coefficient of friction of 0.49. Okay, so we started this problem by noticing that our speed changed and there was some force causing us to slow down. So our speed change, that is a change in kinetic energy, and it must be that that change in kinetic energy was due to the work done by some force. So we used our definition for work to find the work done by friction, and then set that equal to the change in kinetic energy, and that allowed us to solve for our coefficient of kinetic friction. Okay, then we had to use some Newton's laws in between to find that the normal force was just equal to the weight, but that's relatively simple since we're on a flat surface. Okay, so that's it for our work problems. I hope this helped. If you have any problems that you may want me to work, post them in the comments, and maybe we'll do some more videos since work does tend to be a topic that gives people a lot of trouble. So I hope this helped.